All right, guys, our next speaker is going to be Steffen Gielen, who is going to tell us wonderful things about Hamiltonian GR with and without Weyl invariance. Steffen.
All right, thanks a lot, Dave. Thanks, Sean, for the invitation. It's a great pleasure to be here, and thanks to all for still being here and sticking around. I guess I've been to quite a lot of these shape dynamics meetings, as I've been reminded by a few people. And yeah, it's always nice, of course, to see what's going on. I'm myself an outsider, I guess, to this community, but I'm actually trying to pick up on some of the ideas and understand them from a slightly different perspective. So I think the talk will mention a lot of concepts that have been discussed by other people in the last 2 days. Hopefully connect to what other people have said, but really from a slightly different perspective. So I guess same questions about shape dynamics. What is shape dynamics? Is it different from GR? There's some local, it's locally equivalent, but global differences. What does it mean? Can we understand from a standard physics 4-dimensional Lagrangian perspective, where you have some fields and some action? This is always what we're used to, and so we'd like to understand perhaps how the ideas of shape dynamics can be formulated in this. I'm just telling you about results where we were thinking about different formulations of general relativity, which have all been studied by other people, which are, as I said, all locally equivalent. They have different fields and different symmetries. Hamiltonian perspective, and in particular, of course, the symmetry we're looking at is Weyl invariance, so local scale invariance, as it's been proposed as a fundamental principle in shape dynamics. So this is joint work with Roberto Percacci, and Rodrigo is a student of Roberto at CISA. The paper is, in fact, written essentially. We just haven't put it out, so this talk is basically your opportunity to completely shoot me down and tell me about all the fundamental flaws so that we can perhaps rewrite the paper before we put it out. But yeah, it should be out this month, hopefully. So this is just to explain the historical background of this work. And in fact, this basically started a year ago, so pretty much exactly 1 year ago. A workshop on shape dynamics at the Perimeter Institute, and I happened to be there, and Roberto was an invited speaker, and so we started discussing the question that I already just mentioned. And the question is really, we look at shape dynamics. It's a Weyl invariant version of GR, which has a preferred foliation, and can we relate that to spacetime covariant and Weyl invariant formulations of general relativity? And Roberto always has a favorite that he talks about, and I think talked last year exactly about this formulation, which he attributes to Paul Dirac. So Dirac wrote this paper in 1973 that is mentioned here, and he wrote down a formulation of GR that is Weyl invariant and functional Diffeo invariant and locally equivalent to GR. And so it's somehow an obvious candidate if you want to make shape dynamics sort of covariant in some sense. And so this question of what exactly the relation is fairly sort of straightforward to ask. And so that's what we study. We have some partial answers. I don't really have a complete equivalence in any way, but I think, many of the more general concepts that were discussed in all the introductions to shape dynamics can be discussed here. So theories can be related by gauge fixing or by gauge unfixing, which physicists usually call like the Stückelberg trick. You introduce extra fields to sort of enlarge your symmetries. We have symmetry trading, where somehow two formalisms can be related to one another by exchanging symmetries. And all of these things will appear here in a slightly more context. So out again to the organizers of the last shape dynamics workshop. I think this is Enrique and Dave, right? And people who are not here today.
Not really Dave. Yeah.
Yeah, okay. Actually, I checked the Perimeter website to see Dave's name there. So he gets the credit, apparently without having done anything. Okay. All right. So yeah, just an outline of the talk. I will show you how you can make general relativity Weyl invariant in a fairly straightforward way. This is known to many of you, but just to introduce the ideas here. And this Weyl invariance is fake in the sense that I will make clear in a moment. So I will just tell you how that works. Perspective on general relativity that is different from the one that is normally presented to us, and at least incorporate some of the ideas that Hermann Weyl had about so the fundamental structure of physics. I will then do some discussion here in the Lagrangian setting, where I'm just relating different formalisms for GR, different, as I said, locally equivalent formulations of GR, and there's a nice circle that you can draw in which different formalisms are related to one another. I'll just show you how that works. The main technical result is really in this third part, so that was sort of the calculation we did. So D is this gravity formalism. DG can also stand for dilaton gravity, because that seems to be a more popular way of theory, so we just leave it as DG. And the calculation was just out the Hamiltonian analysis. So I'm just going to show you what we got, and maybe some surprises or sort of that we can discuss in a bit more detail. Then there's various ways of theory, which I will discuss. And then the main idea that was also in the abstract is that this Dirac formula provide perhaps a sort of link theory between GR and shape dynamics, which is again something that of course has been discussed by of shape dynamics. And then I'll summarize. So Hermann Weyl emphasized that the relativity GR should really be extended further, right? So we are all fact, and again this has been discussed by others, that notions of space and time are observer dependent in GR, not absolute, but we still have something that is absolute, which is the notion of scale, right? So observers at different points in the universe all seem to have the same standards of length or momentum or mass and things like that. So this is in a way questionable, and you might seek a more fundamental description in which these absolute standards do not exist, and in fact I would be allowed to change the units locally at each point. So in GR, one of the ways of seeing that there are such universal standards is that the metric is preserved under parallel transport, right? So if I take the and sort of transport that, then I will get the same result at a different point. And in fact, you can take this equation as a starting point and try to generalize it by changing the right-hand side from 0 to something else. And Weyl's idea was in fact define a more general type of connection that only preserves the conformal structure, right? So that's exactly the thing we are looking for. Think about the same question sort of more mundanely. You just observe that general relativity provides you with a dimension for constant, which is Newton's constant, which you can then use to define units that you might call natural, and these are the same everywhere. And in fact, this is one of the first observations that Planck made in this paper, 1899, where he introduces Planck's constant, and so the quantum of action, and observes that you can now write down units of length and time anywhere in the universe. So that's actually explicitly stated in this paper, and its constant comes with units. So what you do in this Dirac formalism is quite simple, and it's in fact a version of this Strickle metric. So you make general relativity Weyl invariant by introducing a new metric that is conformally related to your original space-time metric. So this metric, you just write that as so phi squared, and you have this constant here, which is just so the dimensions work out. And in fact, you can just substitute this into your Einstein-Hilbert action, and you obtain the action of what I call DG. So this is again Dirac or dilaton gravity. So this is your Einstein-Hilbert action written in terms of this metric G bar. And now if I just substitute this, I end up with this kind of. So you have this coupling here between the Ricci scalar and phi. And then here you have a kinetic term, and the coefficients match just to a conformal invariance.
Clarity.
Mm-hmm.
Is phi a function of position or not?
Yeah, phi is a function.
Like
Yeah.
a gauge field.
Yeah, I mean, I'll mention this in a moment, but yeah, you can. I mean, it's a redundancy in your description for sure, because of course G bar can be written as phi and G in an infinite number of ways that are. Yeah. It's a trick that is completely standard in physics, right? I just want this additional symmetry, and here I'm just sort of enlarging the space of fields by hand, and of course by construction I then get the symmetry I'm looking for, which is Weyl invariance, right? Because G goes to omega squared G, and phi goes to omega to the minus 1 phi, leaves this invariant, leaves G bar invariant. So here I've made explicit that this is space-time dependent, but these are all space-time fields, right? Okay, so you can also check explicitly that this Lagrangian has the symmetry, but it's kind of obvious if you look at where it came from. And it's of course also space-time covariant under four-dimensional diffeomorphisms. You can do this in any number of dimensions, but I guess 4 is most interesting. Now, terminology, the Weyl invariance is fake. Apparently this was a phrase coined by Jacques, who studied sort of certain currents, Noether currents, and found that they vanish. Simple way of thinking about this, you can of course remove the invariance by local gauge choice, right? For example, I can just set phi to a constant in space-time, and then I've removed this symmetry, and this is different from a normal gauge symmetry as we are used to in Maxwell theory or in Young-Mills theory, where of course I would make the description non-local necessary. So in a sense, this is a much more real type of symmetry than sort of a proper gauge symmetry in some sense. So I think we still have to agree on whether we call this fake or something. This distinction between different types of symmetries should be hopefully clear. So yeah.
No, I was going to say that you can say that you can just fix it to something and fix that symmetry because you know where it came from. Otherwise, you'd have to go to some process to know that you are allowed to do that, and that will fix the symmetry that you wanted to fix.
Right. Yeah. No, sure. Yeah. This is obtaining this description by starting with a description that doesn't have this symmetry. So this is, in a sense, much more trivial than a more general construction would be. Okay. So this action is a genuine action for general relativity, right? I mean, at face value, this looks just like a conformally coupled scalar field, but the point is, of course, that the metric G is also dynamical, and in fact will just satisfy the vacuum Einstein equations. Well, G bar will, so there will be a conformally transformed version of the usual Einstein equations for the metric G. Okay, so this Weyl principle of gauge freedom, I mean, this is of course where the name gauge freedom comes from, in fact, which corresponds to this choice of units that you're allowed to make at each point in space-time, is sort of implemented in this function. And in fact, that is just the role of this field phi, right? So the field phi has units of mass, and so it takes a particular value at each point. So that will then set your local standard of mass, if you want. So you can choose it completely arbitrarily. Of course, if phi ever goes to 0, then you're really in trouble. So another point, of course, is that now the notion of what is a geometric singularity is invariant under conformal rescaling, right? So my original metric G bar might have a singularity, and in particular cases, I might be able to shift this singularity into phi goes to 0 instead. So this is something that you can do in cosmology, for example, right? Where your scale factor goes to 0, you can just shift that into this field phi, and the metric G can be completely regular, but you have to live with the fact that phi goes to 0. And then you can say that certain singularities are resolved classically. The point, of course, is that this is only physically significant if the matter fields now couple to G and not to G bar, because G bar is, of course, still singular. So you have this freedom in choice of matter coupling, and this is of course well known in the literature on modified gravity theories, where you always have this question of what is the metric that the matter fields couple to. And this, you can see this as an example of a scalar tensor theory. Okay, so these were just some remarks to show you that there is this very nice, relatively simple formalism that is locally completely equivalent to GR, but now implements this principle of local scale invariant. So what do we do with it? You can view it sort of, if you just look conceptually, as a new perspective on general relativity. Physically, nothing in what I told you so far differs from what you could do in standard GR. But one of the points I would like to make is that there's a practical use in connecting different local formalisms, in providing if gravity just put in there. So it's a background if you want. This action, of course, because here you have the wrong power of the determinant of G, this breaks the invariance of GR, the full diffeo group, to special diffeomorphisms of volume diffeomorphisms. Now get this additional Weyl invariance. So you scale G, again by space-time dependent function, this action will be invariant. Okay, and this is where this name comes from. So W is a Weyl, and T diff is transverse diff is the same as these special diffeos. So this looks pretty complicated. It's again just a normal action for GR, locally equivalent. To check that this corresponds to any of the actions you might be familiar with is quite complicated. But here in this DG formalism, it's quite straightforward because you just have to choose this particular functional form for this field phi. Right? As I told you, phi is completely arbitrary, it's pure gauge. So I can, in particular, choose this form. Right? So omega is just this background that I've assumed. It's just some given scalar density on space-time. And then I sort of make this combination here. And then if you again make the substitution, you will find this WT diff gravity action. So yeah, so this is just to show you that sort of this can help you and explain the relation between different formalisms of GR. And in fact, that was kind of the first thing we did, was to look at this so-called circle of theories. So here we include all kinds of unimodular formulations of general relativity. And by unimodular, I mean, again, it's kind of fortunate that this little omega has appeared in other talks, so the notation is consistent. That's just a coincidence. A lot of people would call this, would set this to 1, right? They would just say square root of G is 1. We don't really like that for various reasons. For example, it means the metric must be dimensionless and all kinds of other things. So here you just say you have a fixed scalar density omega, and if you impose this additional constraint, that's what we call unimodular.
And that only has meaning, it doesn't have a different invariant meaning under WT diff, does it have a meaning? That's the, that you fix where
yeah, well, this always breaks diffeos to special diffeos. So if you've already broken them, then either this is true or false. Then you can't do anything else. If that makes sense. Yeah. So this is the diagram that you get, right? So you can start from this DG formalism where you have a four-dimensional, well, space-time metric, and you have this field phi, and the symmetry group is diffeos and Weyl transformations. Just setting phi to a constant gives you Einstein gravity, which is invariant under diffeos. Just setting the metric determinant equal to this density gives you UD, which is unimodular Dirac or unimodular Dirac gravity. Now you have this field phi, but you also have a unimodular metric. Actually, the symmetry group is still the diffeos. They just act in a funny way. I can explain that in detail, but it's not too relevant at this stage. And which G to unimodular gravity. Yeah.
So physically these are all
these are all the same theory, but they are different starting points if you can go beyond ordinary general relativity, right? Is that
That's one way of saying it. I mean, they're locally equivalent. So there will be global options to making these choices, like for any gauge fixing. Locally, they're equivalent. As an add further, presumably these formalisms would allow different types of terms to be added. But,
what is EG? Sorry.
EG is Einstein gravity. So that's just your Einstein-Hilbert formalism. Yeah. So we just have these shorthand. A UG is unimodular, and UD is unimodular Dirac or unimodular dilaton. Yeah. Sorry. Yeah. Okay. So in this sense, sort of in this Lagrangian picture, everything is quite nice and straightforward. You can say it really is a kind of linking theory, right? These three formulations, if you compare them, they all have the same number of dynamical fields and the same number of symmetries. But yeah, getting between them, sort of finding the transformation that relates them to each other might be quite complicated. But if you observe that all of them come from this DG and just under different gauge choices, then this is much more straightforward. And yeah, at the end of the day, if you want the smallest possible group of symmetries, you might prefer unimodular gravity. But again, sort of the preference you have depends on various things that sort of are associated to the kind of redundancies you would like to have in your description, to the validity of these gauge fixings that typically are not globally viable, and all kinds of related to quantization, you might prefer one over the other, and so on and so forth.
In unimodular gravity, you are seeing as a gauge-fixed version of GR.
Mm-hmm. Yeah, I mean, you basically fix the diffeos that change the metric determinant.
So we have to always remember what's the transformation property of omega, right?
Omega is just fixed. This is a background. It's just a fixed function on space-time. I mean, it depends on how you look at it. That's right. It's a bit subtle, whether you allow yourself writing it in different coordinate systems and so on and so forth. So yeah, I guess a more useful way of thinking about it is that it's a given form on space-time. So of course that can still be written in different coordinate systems. We'll probably discuss this more later, but yeah.
Am I right that this is something to do with the cosmological constant, and that you've actually the left-hand side of the Einstein field equations is not quite what it was before, and then you rectify things by bringing in the energy momentum tensor?
Yes. So
that's correct.
George knows this. George knows all of this much better. But yeah, the point is, I mean, here I'm just gauge fixing, right? I'm just saying I start with Einstein gravity, and then I impose the metric to be unimodular, which I can always achieve locally by a diffeo. Of course, if I start with unimodular gravity as sort of the fundamental description, logical is kind of an integration constant, and it's different classical solution, and is not something that I can fix in the action. Yeah, I think I wasn't going. Yeah.
Shows I listen to George.
Good. Right. So that was just this circle of theories that I wanted to show. These things are, as I said, straightforward. And the question is something similar in the Hamiltonian setting to shape dynamics, which of course I haven't mentioned at all up to this point. So yeah, said you can look at the circle. You can say there's some linking theory here at the top. You can say there's maybe some symmetry trading going on if you relate these different formulations of each other. I know technically the same term that has been used, the shapists, but that's why it's in quotation. And everything has been Lagrangian and space-time covariant. Okay, so study theories that have a preferred perhaps, and so we want to introduce a Hamiltonian formalism. And in fact, we kind of expected this to be the literature, but apparently it wasn't. There was a correspondence between Karel Kukasz and Julian, actually, that I should probably discuss with you later, related to this topic. But anyway, so no, there's a private communication between Karel and you. Yeah.
It's a 64-page letter.
Yes. But yeah, certainly there's no published work that would settle this question. So we just did it from scratch, essentially. That's So now I'm just integrating by parts. Conventional form, dropping all boundary terms, so boundary terms are just ignored here. And you do your 3+1 decomposition. A note here is that this is a special case of Brown-Sticker gravity, where the +6 would in general be a -4 omega, where omega is this dimensionless Brown-Sticker coupling. And again, as is known to people who've looked at Brown-Sticker theory, if you take the limit, omega goes to -3/2, you have this additional Weyl invariance, and you lose degrees of freedom, would otherwise be in the scalar field. So you would think that perhaps you can just take what's been done for Brown-Sticker theory and take this limit, but this doesn't work. This limit is singular because you have the Weyl invariance that just appears in this limit. Again, that's why we had to do it from scratch here. So I don't want to do too much with the technical details, but I'm just going to show you the most essential features here of canonical analysis. So you what you always do, your dynamical variable, metric, and the scalar field, lapse and shift, are not dynamical, and you can use Lagrangian multipliers. So you introduce these canonical momenta here. So Pij is a momentum for the 3 metric, and I is a momentum for the scalar field. From the Lagrangian is the extrinsic curvature. K is just the trace of the extrinsic curvature contracted with the 3 metric. And this partial n here is for the normal derivative along the normal to spatial hypersurfaces. Yeah, again, these quantities will be familiar to anyone who's looked at canonical T. But now the point is that you immediately find a primary constraint, as you would expect, right? So if you may not see this immediately, but if you contract this one with Qij, you multiply this one with phi, and you add them with the right coefficients, you find that you get 0. And so they are actually not independent, right? There's a constraint between these momenta, so you cannot invert the velocities uniquely in terms of the momenta, and something you have to deal with in doing this canonical analysis. And this is, of course, exactly the constraint that generates Weyl transformations, right? So that just tells you in the Hamiltonian setting that you have this additional invariance. Okay, so now you have primary constraints. As usual, they tell you that the conjugate momenta to lapse and shift vanish. You look at the consistency of these under time evolution, and you get the Hamiltonian constraints. This is exactly the form you would expect. That just tells you that phi transforms as a scalar and the metric transforms as a tensor under diffeomorphisms in space. So these are just space diffeomorphisms. And then you get this additional constraint here. Yeah, so the P tilde, but yeah, here just the trace plus respect to the metric. These are the usual you would expect to see in this Hamiltonian constraint. The point is that because of this primary constraint, there's now an ambiguity in these expressions, right? So here I have this term involving pi, the momentum of the scalar, but I could have replaced that using this constraint, sort of in terms of p over phi, for example. That would also, right? So I have this freedom of substituting variables in writing down a complete dependent constraints. And here, basically, so the reason why I've chosen this form is essentially just that if you ignore the first term and only look at these ones, that would be the Hamiltonian just for the conformally coupled scalar on its own, right? So because it comes with the wrong sign kinetic term, it's kind of a ghost, so it has this kind of, but this is exactly the usual you would expect, and this is sort of the potential, if you want. But this is, of course, a purely aesthetic choice, because pi is not independent from p, and I could always using the primary constraint, right? Okay, and so the usual thing to do would be to fix these ambiguities by demanding that these 4 constraints satisfy on the as the hypersurface deformation algebra, so they do correspond to the geometric action of 4-dimensional spacetime diffuse, so 3-dimensional diffuse within a slice and sort of a refoliation. So that's what you'd like to have, and basically we find that this seems to be impossible to achieve. So, this form doesn't do it. If you compute the Poisson bracket of h with h, you do not get what you would like to have. And basically, the general result is what I'm giving here. So, the point is, as I said, to have a Hamiltonian constraint or have a constraint that you interpret as generating refoliations.
Do you get the other brackets to fine, or is it just the HH?
Yeah, the other ones are fine. So d with d obviously works because this is just the form you have. And d with h works because h has the right property, transforms in the right way, is a scalar density. So these are, in a sense, obvious. The only one that's not obvious is h with h. Yeah, thanks. Right, so that's the only one that you really have to check, and of course that's where the work goes in, actually doing the calculation. Just a general result. So imagine, I could do sort of just trial and error, of course, use this primary constraint and rewrite terms in some arbitrary way, but I could also just try to do something more general. So I'm just writing down these terms here, and I just assume that my Hamiltonian constraint is just a linear combination of these terms. So these are all scalar densities as they have to be. They have to have the correct conformal weight. And they're basically all the terms that I'm finding here, and I'm also adding just this mixed term here, this p phi mixed term.
Sorry, now you're just going to use these terms as basically a basis to construct another.
Yeah.
But you can't get to this basis just by exploring that extra constraint that you have, right? This is something different that comes from that Hamiltonian. Right?
No, here I have. So if I write this out, I have a pij, I have a p squared.
Right.
Here I have a pi squared, and then if I use this constraint once, I can replace 1 pi by a p over phi, and that's all the terms here. And yeah, the last three ones are just the ones coming from here, so these are the same. I don't use any extra terms that I wouldn't.
Is that for me it's not clear that you would be able to get independent coefficients in each one of these terms just by using that.
Yeah, you don't. No, you don't. So the approach is different. I'm just. I don't want to waste time manipulating this constraint. I just start anew. I just take an arbitrary combination and I see which forms are allowed if I demand that I want the hypersurface deformation algebra. And I would expect to see a response to what I want. Okay, so yeah, so that's the statement here. You would sort of take some linear combination of these terms and you impose this constraint here. That sort of the commutator of two of these h's should just be a three-dimensional diffeo with this typical form here. Okay, and what you find is that there's essentially a unique form here up to a free parameter. So there's this free parameter a. These are basically the terms I had before. C is the conformal constraint, so you just add this sort of function times c squared and you get this new term here, okay? And so the point is that this new term, of course, now breaks your conformal invariance because it will change the coefficient of this term here. And so in fact what you can show quite easily that this is just Brown-Sticker gravity, where this a is related to the omega I had before, okay? And so again, if I want to do the limit where omega goes to -3/2, that would be a to infinity. So I'm kind of screwed because this term would blow up. And the same thing happens with other ways you can try to construct the Hamiltonian constraints. So for example, there's this work by Bodendorfer, Stockmeister, Thurn on GR coupled to a conformally, GR with a conformally coupled scalar. So you have an extra Einstein-Hilbert term, you try to remove that, you have exactly the same issue, that one of the terms would blow up, and I don't really know what to do. So the point seems to be, if I take this form of the Hamiltonian that we had originally, the Poisson bracket of two of these constraints always gives you this additional Weyl transformation. So I mean, you're still sort of fine, you still have a first-class algebra, you're not generating any funny additional constraints, the number of degrees of freedom is the same as in GR. But basically what this means, or what this seems to mean, is that generate usual diffeomorphisms, but the diffeos that you generate always need to be corrected in some sense by a Weyl transformation. And this really seems to originate from the fact that this whole formalism was derived from an original Einstein-Hilbert theory just in terms of this metric G bar. And of course, if I do diffuse on G bar, they won't be diffuse on G. So perhaps this is obvious, but this seems to be something that cannot be avoided. I'm not able to identify a nice subset of constraints that only does four-dimensional diffuse and nothing else with Weyl. So I have these 5 constraints, right? So I can write down H, D, Di, and C. That's 5 constraints. And they're first-class algebra, so I'm happy. I'd like to identify 4 of them that just do diffuse and nothing else. Yeah.
Yeah, maybe I'm just too naive, but isn't that extra term not just expressed is not 0? It means that if you go that you have you don't just have the hypersurface deformation, but you have to compensate for the fact that in different slices you have different phi's. At different values of time you have different phi's. Is that?
Yeah, you could see it like that. Yeah. Mm-hmm.
So I wouldn't be bothered by it in that sense.
Okay, that's good. Okay, so that's just the result of. Yeah, we can discuss it more, but I guess I should finish my talk now. Now the question is, okay, you have this sort of Weyl invariant formalism now at the Hamiltonian level. What are the different gauge fixings you can look at? And in fact, the ones that we discussed before in the Lagrangian picture, you can sort of write them down straightforward in language. So again, if I want to go back to Einstein gravity, I add this gauge fixing condition saying that phi is a constant. And you can say that this is a global standard of units of mass that is now given by this constant here. This is second class with the conformal constraint, so it fixes the conformal constraint, and I just get ADM. So this is nice. And unimodular gauge condition, there's some literature on how you should impose them. You can see them just as a choice of lapse, right? So if I choose the lapse to be like this, that satisfies what I wanted in the beginning, because now n times square root of q is omega as required. Do this a bit more formally and enlarge your phase space again to include the lapse and its momentum, and then do a proper gauge fixing. But you don't really add anything too deep when you do that. Maybe more interesting is at least some partial relation to shape dynamics, which is this Lichnerowitz gauge. So here I'm just adding a constraint that says pi should be and of course by the conformal constraint this is the same as maximal slicing. You can show that this now fixes the Hamiltonian constraint, so it fixes the refoliation invariance. You get the Lichnerowitz equation for phi, and you get the corresponding lapse fixing equation for the lapse n. So none of this is particularly surprising, but here you just get this directly from a gauge fixing of this Hamiltonian sort of DG theory. And the constraints you are left with would then just be these ones that tell you that this momentum Pij must be transverse and traceless with respect to Qij. And again, that's of course what you are used to from the Lichnerowitz method. So you have to solve the Lichnerowitz equation and relate the solution that you find for this field phi, would then relate your Q and P to the corresponding Einstein frame quantities in the usual way. Right? So this is, again, is nothing new at all, but it's just sort of from a different perspective. Of course, the question would be to generalize this to the York method at least, and allow more general types of gauge fixings, which is more complicated, and so we actually haven't done that so far. Okay, so now just, I guess the timing will work out quite nicely. I just have one last thing to say. The question was always, can this now be a linking theory for GR and shape dynamics? Of course, this can only really work in very special cases. So I've opened Flavio's textbook here. I don't have his pictures, but I've stolen his equations at least. So this is a linking theory for shape dynamics, which I guess was written down in the early days. Here written in slightly different variables, which are the variables that we are using here. So you have again a theory of a three-dimensional, well, a spatial metric, a conjugate momentum, scalar field, and a conjugate momentum for the scalar field. you have a diffew constraint, you have a conformal constraint, and you have a Hamiltonian constraint. And these constraints involve these kind of spatial averages here, right? As they usually do in shape dynamics. And of course, spatial averages, so you have to assume that they take particular values if you really want an exact equivalence between this formalism and what we found. So this is one case. In general, of course, you would try to find a canonical transformation that relates the two. And again, is something we haven't done. But at least sort of in these special cases, the two are exactly equivalent. So this linking theory that was constructed previously by purely Hamiltonian methods is actually just sort of this very simple kind of space-time theory that sort of Dirac. Let me summarize here. So I introduced DG, which is a invariant and space-time covariant theory for scalar. I think I meant to say Lagrangian metric. You can get this from Einstein gravity by the Stückelberg trick of writing the original metric as a function of the new metric and the scalar field. You can show in the Lagrangian setting quite nicely that there are different gauge choices that reduce DG to various known formulations of GR that are locally equivalent. We did the Hamiltonian analysis, and we found it impossible to separate sort of a subset of constraints that only satisfy the surface deformation algebra. Space-time diffeos always mix Weyl transformations in the setting. And then we looked at various gauge fixings, including this Lichnerowitz gauge, which is the case of maximal slicing. And so in these special cases, at least, we can also get a linking theory for shape dynamics. And we ignored all boundary terms, and we don't have a global Hamiltonian, because our conformal transformations are not volume preserving. Okay, thank you.
Okay, we've had a couple of questions already, but student questions first. Not a student.
If you say actually your theory is a linking theory, I mean, if in that case you have to, I mean, if you extend it to actually in the all general physics, not only gravity, do you have to actually express the coupling constant with the phi?
Yeah, you can lift the entire standard model to this picture if you want by just sticking in appropriate powers of phi. Because phi is just your local choice of units, right? So you can just express all couplings in the standard model with respect to G Newton, right? And then G Newton becomes a power of phi. So that's been shown by various people that you can do that, but yeah.
Further student questions? Okay, we'll open it up to general questions.
So if you go back to 17, the last slide, like, okay, maybe you know this already, but you kind of half said it, but like, I'm not too surprised that you didn't get the conditions of the mean, because when we did the our compensator field, we explicitly oppose volume preserving condition of phi.
Yeah.
So what you would just have to do, I would expect what you'd have to do to get that is to find some analog of that condition on the space-time. But I doubt that a canonical transformation is going to get you there, because I mean these are really different constraints that give you different. I mean maximal slicing and CMC are they cover completely different kinds of space-times. So
Yeah. So I'm of course familiar with what you did, and the difference is quite obvious, and I don't yet know how to relate that. So yeah, that's all I can say at this point.
I know Enrique and Julian have got perturbations on this question. Is your question also a perturbation or a simple?
Very quick comment, but it's
Okay, well we'll go with these next time around. Julian.
I just wanted to check the answer. Basically, it seems to me these conditions are recovering certain solutions of GR, but not all. Maximal slicing is okay in asymptotically flat space-time, isn't it? So it's, I think that's what it is. I mean, you've got no dynamics in a spatially closed thing. So it's a device for picking up particular types of solutions. And in fact, R1, by taking your condition, I mean, early on I thought, we would just pick all the solutions of general relativity which are CMC fermiable all the way through. Now I'm a bit more modest and think, well, if we can at least pick up those that are CMC fermiable in the immediate vicinity of the Big Bang, that will, so to speak, specify, that will be a set of solutions that will, in a minimal, non-redundant, scale-invariant way, specify initial data, so which will never get lost, however the system evolves. And that might be a more modest way of looking at it. But it seems all of these things are ways to restrict the number of solutions allowed by full general relativity. And a lot of people feel that that's quite a good thing, because a lot of people think there's far too many possible solutions of GR.
Yeah, so this is of course restrictive. There will only be very few solutions that admit this gauge fixing, as all of you know. So this doesn't really add anything new to this known statements about the Knarowitz method, right? It's only applicable in certain restricted cases. And of course here we threw away boundary terms completely, so this most naturally only applies to, say, a closed universe which doesn't have a boundary. And then, of course, the maximal slicing is extremely restrictive.
Sorry, mine is just a technical question, and maybe I'm a bit mistaken and I forgot it. Can you go up one slide, please? So my impression was that the Q constraint there, at least I don't know exactly what parameterization of the variables you're using, but in the original we had just pi minus that minus 4 pi minus mean pi squared g, no pi phi. Right, to the new scalar. Ah. No, I know. Okay.
But this just generates conformal transformations. Yeah. Yeah, exactly. Yeah, exactly. So if you're right, if you go to the exponential parameterization, this will look slightly different.
This is no clear. Yeah. Questions?
Just a brief comment. I presume you're aware of the work of Erhard Schultz about Weyl geometry.
I'm not sure about that.
Okay, you should just look him up. He's at Wuppertal, and Erhard Schultz, SCHOLZ.
I will do.
Thanks. I just want to pick up George's thing because George is a very nice person and a considerable historian of what Weyl did. And he spent a few days with me and Friedrich Hale at my home, where it transpired that he was a much better historian and mathematician than a physicist. He didn't really know about Lagrange functions, it turned out. So just to be warned about that. But I mean, his papers are certainly well worth reading. I think there's a lot of valuable information in them.
Further questions for Steffen? Going once, twice. Okay, in that case, let's thank our speaker again for an excellent talk. I'm going to make a suggestion we just plough straight on since this is the last talk. Then we'll share with that we can do, but I think
You get the easiest name to pronounce then.
yeah, I figured
That's what you know, I'm sure you know that.
So that's the
Oh yeah, what should I do with it? That's fine.
that's correct, or
It's fine.
Can you pronounce it once for us?
Doboszewski.
Full name.
Juliusz Doboszewski. Yeah, well, that's actually a Polish accent anymore. Yeah.
it's almost like England pronounce their own names.
It doesn't work. Let's try it in here. Yeah.
So there's always
get back there.
Yes, that's the last one. The super last one. Oh, this one. Perfect.
Where's Sean? Do you mind batting with the camera and stuff then, Sean, since you're the other one who knows how it works?
Yeah.
I see.
It's on.
Is the microphone switched on?
I have no idea.
Yeah. We're good.
But this one doesn't work yet?
No.
Oh. Really? Cool.
Okay, so our final talk of the conference is Juliusz Doboszewski, who's going to talk about, well, he originally said black hole, white hole transitions, but I think we're having singularity resolution.
That's not me. That's what Sean did. It's actually what it's about, so it's
Okay.
also fine.
Excellent. Okay.
Yeah. Thank you. Yeah, thanks to Sean for having me and for you for being here still at this time. I promise it will be short and perhaps a bit provocative at some point. So, yeah. Let's see how it goes. So I plan to do it in the following way. I will have a few brief remarks on singularity resolution and what could it amount to. Then I will discuss a particular singularity resolution model for black hole spacetimes. Super briefly compare it with cosmological singularity resolutions, and then discuss so-called white hole instability results from the 70s and 80s, and I guess 90s, and see how they could be used, and argue that they could be used in constraining these sorts of proposals. And then there will be a speculation about generalized second law at the very end. Okay, so we do know that for a variety of reasonable physical situations, classical GR predicts singularities. And of course it's a classical theory, it's not a complete theory of the world has quantum aspects, and the hope is that, well, perhaps quantum aspects of the world, of matter fields, will somehow prevent or resolve some forms of singularities. So what exactly could that mean? Well, perhaps some quantum gravitational theory will provide us a description of a process which prevents curvature blowup. I think this is how most of the physicists conceptualize singularity resolution, but certainly not all of them. Of course, a super minimal version of what singularity resolution is, it's just an argument to the effect that some of the premises of some of the relevant classical singularity theorems fail in some given context. But that's of course not enough. Ideally what we would like to have, for instance in case of Big Bang type singularity, is a construction of an extension through some type of a horizon or through some sort of boundary in space-time in such a way that it makes sense to talk about time-like or null and space-like geodesics in the region through which we extend the space-time and in the additional regions. And the extension is done in such a way that curves which are incomplete in the classical solution become complete in the extended solution. But if you look at some particular context, such as context of black hole spacetimes, singularity resolution could simply amount to some description of late stages of black hole evaporation, assuming that black holes evaporate, and I assume that for the time being. And this description of late stages of evaporation should contain some solution to the information loss paradox, which is not just that black holes fully evaporate and we're left with a naked singularity. If we're left with a naked singularity, then of course we do not have a singularity resolution. And perhaps what singularity resolution could be is just a description of some physical process which prevents formation of some sort of horizon, say event horizon in case of gravitational collapse. Now, in some cases, we do few of those simultaneously. So I think when we have something like extension through the Big Bang singularity in quantum cosmology, we do first 3 simultaneously, and of course we don't bother about 4th and 5th. But I think it is important to keep it in mind that not all extensions through the Big Bang will be a good candidates for singularity resolution. So here's a cool recent result in mathematical GR. In case of some open cosmological models, one can construct a C0 extension to the initial singularity. So that's merely a continuous extension.
Then Einstein equations you can't use.
It doesn't even make sense, right? It's just a C0 extension. So those spacetimes are C2 inextendable, but they are C0 extendable. And such extension can be constructed, and in a way it could be shown to be unique. But in this extension, there is no reasonable notion of something like distinction between time-like and null and space-like curves. There's no notion of a geodesic. There is no way to even make sense out of Einstein's field equations. And so these sorts of results, of course, even though they provide us with some sort of extension through the cosmological singularity, would not be a decent or reasonable candidate for singularity resolution. And I don't want to suggest that they are meant to be so, but I think it's an interesting example which stresses out that those additional conditions are really important. So now I will be mostly focusing on black hole singularities. So ideally, what we would like to have in in case of black hole singularity resolution is perhaps all 5 of those conditions. And I think minimally, at the very least, we should have the 4th one. So we should have some answer to the information loss paradox, which does not leave us with a naked singularity. Because if we have that, for the purposes of observers like us, whatever happens inside the event horizon, that's none of our business. We only care that we do not see something like a naked singularity. And the particular proposal I will be focusing on, which I will be calling black to white hole transition. So that's the idea some of you may be familiar with if you talk to loop quantum gravity people. Like recently, like during the last 2 years, they seem to be pretty excited about this sort of stuff. I think that's a speculative part, but I think a case could be potentially made that in case of this particular type of approach to black hole singularity resolution, we're just left with 2 and 4. So some of the premises of classical singularity theorems will fail, in particular energy conditions will fail, and we will have some answer to the information loss paradox. But I think it's an open, interesting question whether the relevant curves will be complete in the extended solution. And there is a sense in which, like, even if those models do satisfy all 5 of those requirements, they are still not a satisfactory black hole singularity resolution, because those models only work, at least at the models we currently have, under the assumption of spherical symmetry. So in particular, they won't work for curved black holes. There's a general philosophical point I would like to make here, and it's the following. That what is your favorite characterization of what it means for a spacetime to be singular? And what you take to be a physically reasonable spacetime is really important in the context of these sorts of considerations. And so here's an example. Assume that singular spacetimes are characterized in terms of geodesic incompleteness. Not blow up, but geodesic incompleteness. In principle, it would make sense to talk about singularity resolution for something like maximally extended Misner spacetime. I will show you the spacetime on the next slide. But if singular spacetimes are characterized by curvature blowup, maximally extended Misner spacetime, even though it is super weird and it is time-like and null geodesically incomplete, would not even be relevant to the issue of singularity resolution. And so, in this sense, even if you have something like a Big Bang singularity resolution and black hole singularity resolution, you may not have a general singularity resolution for all kinds of singular situations, singular space-time, singular general relativistic spacetimes. You would have rather something like singularity resolution for all practical purposes, so to speak. So this is the spacetime I have mentioned. I have shamelessly stolen this picture from George's and Stephen's book. It's a two-dimensional spacetime which has a chronological and Cauchy horizon at this surface t equals 0. There are, well, sort of depending how you count, one or two maximal extensions of this spacetime. There's no curvature blow-up in here. Sort of, you can think of this in the following way. You have two classes of curves, of future-directed time-like curves as you approach the t equals 0 surface. And in the maximal extension, you can continue one of those in a way which violates causality conditions. So in particular, this extension will have closed time-like curves. But there is no curvature blow-up in this spacetime. And any maximal extension here is time-like and non-geodesically incomplete. So that illustrates my general philosophical point. If you think of singularity resolution as something which provides you an answer to curvature blow-up in some cases, you may not have a general singularity resolution. But then, of course, you can make additional move, which you would have to argue for and say, oh, look, this is not even a relevant model for the purpose of what I'm doing, or it's not a physically reasonable spacetime, or something like that. Yeah?
What other models have this structure where you don't get curvature blow-up, but you do get complete geodesy?
Yeah, they're rather rare. So they're all like Meissner spacetime.
They're no physically...
Depends what you mean by that. But there are no cosmological models, and there are no black holes models that I know of with this sort of behavior. Yeah. So yeah, I mean, this spacetime has been called the counterexample to almost everything. So you may say that it's very special. Yeah. And then, you know, if you think about black hole spacetimes in terms of geodesic and singularities in terms of geodesic incompleteness, Schwarzschild spacetime is geodesically incomplete, and Kerr spacetime is geodesically incomplete. But in Schwarzschild case, singularity is space-like, and in Kerr case, singularity is time-like. So it sort of forms a ring around the axis of rotation of your black hole. And both of those have curvature blow-up. So just to refresh your memory, this is what those spacetimes look like. That's the maximally extended Schwarzschild spacetime, and this is sort of portion of the maximally extended Schwarzschild spacetime, which is supposed to represent realistic, or well, perhaps not realistic, but spherically symmetric case of gravitational collapse. What is important for the point that I will be making about viability of black to white hole transitions as singularity resolution is the observation that in case of Schwarzschild, which is the only case that anyone has been able to do so far as I know, spacetime geometry within the event horizon is rather simple, which is not like the Kerr case, where the geometry is pretty complicated. And it seems that the sort of methods that I will be talking about in the next section will be significantly harder to apply in this case. And I think it's an open question whether this will work or not. And so if it will not work, we would have, I guess, an unsatisfactory situation. We could have a singularity resolution for Schwarzschild black holes, but perhaps not for Kerr black holes. And if so, like, what is it good for? Arguably, all the black holes that we see are Kerr-like anyway.
Can you remind me what is stable the perturbation for the Kerr black hole?
I think it's an open question. So most people tend to believe that the certainly inner event horizon is not stable against perturbations. Yeah. Good. So now that will be the loopy part of my talk. So what loop quantum gravity people are doing, and I should say right now that I neither endorse nor deny what they're doing. I think it's an interesting model, and it's interesting enough that other people also should have a look at it. They sort of shouldn't leave it to them. I guess. So what they're doing is the following. They try to come up with an analogy of the quantum Bunce cosmological scenario. It's just that it's applied to black holes. And there's a physical story and a mathematical story. I will tell you this more physical side of the story first. And I will show you a relevant diagram in a second. So the idea is the following. Assume that we have a black hole which forms dynamically, and then it starts to evaporate by Hawking radiation and lose mass. The idea is that as the black hole loses mass, the strength of additional non-perturbative quantum gravitational effects will increase. Those quantum effects will be confined to a finite region consisting of two disconnected parts, and those quantum fluctuations, if you like, will lead to a repulsive bounce. And there's been a lot of work done on this. So, like, if you have, a spare afternoon, this I think 120 pages in the current stage overview paper will tell you more than you want to know. So under this picture, the life of a black hole looks like this. Black hole forms, evaporates, quantum gravitational effects kick in, and this leads to transition to a time reverse of your original solution. So because we start with a black hole, this will be a white hole. Then we have a white hole phase, and that in the white hole phase, some material is being ejected from the system, so it loses mass even further, and at some point it will transition into ordinary matter. And this transition is a sort of emerging shell, which is an analog of the collapsing shell in the case of standard gravitational collapse. So this is a sort of story that we get, and this is the picture, which I also shamelessly stolen, but not from Flavia. So this here is the standard diagram, Penrose diagram for black hole evaporation. This is what loop people would like to have. So the way they construct this is the following. We have two regions, A and B. A is within the on the diagram it's an event horizon, but conceptually Carlo will insist that it's just an apparent horizon, not an event horizon. Let's not go into that debate. And we have the second region B, which lies outside of the horizon. And what is being done is basically the following. We take something like a Kruskal solution, truncate it in a way, and then do the same to its time reverse, and glue them together through a region which is a smooth geometry, but which violates Einstein's field equations. But the violations of Einstein's field equations are confined to these two separate regions. And as you see, the diagram is not super accurate. I think you cannot really see it, but there's this is the event horizon, this and this, and here is a very tiny, like a sort of blob which goes like this, which represents what happens to the physical system, which collapses and then expands again. Sure.
It looks like you now have a naked singularity, right? You're in the future of the region A.
Excellent. Good. So there is no singularity here, in the sense that we have, we glued those solutions continuously, and it certainly violates, well, sort of by construction, violates Einstein's field equations, and so in particular, it violates null energy conditions, so it also violates all the stronger energy conditions, and so in this sense, it violates premises of classical singularity theorems.
Okay, but so yeah.
And
to clarify the question,
Mm-hmm.
I mean, even if you say the singularity has been resolved, you would have to have some deterministic dynamics in the region A, right? If you say
Good.
an invariance no longer holds, something else has to hold, right? And typically in these models, that's not made explicit.
No. I think actually the dynamics in those shaded regions is not deterministic. It's rather stochastic dynamics.
And for practical purposes, it's exactly like a naked singularity, right? Something resolved is not
yeah, that's a good point. I wanted to follow up. So, yeah, I actually wanted to ask, so how do you decide what the boundary conditions are on each side of A? Because I think it's related to Steffen's question about how would you continue it? If one side is not determined by the other, how do you decide? And if it's arbitrary?
I think that's a good point. That's one of the things which I'm not really satisfied in those sort of models. It seems to me that this is just done by hand, sort of know what we would like to get, and we sort of construct all the transition amplitudes in such a way that it will ensure that we will get what we want. So it's much less impressive in a way. Yeah, I agree. But one can say that it's not a singularity in the following sense. Take any geodesically, well, take any incomplete curve of the relevant sort in this diagram, and what will happen as you move to the extended solution is that it will enter this region, so it will get some smooth continuation, and then it will get another continuation through the time reverse. So in that sense, it is a singularity resolution. Or on the face of it, it is a singularity resolution. There is a lot of assumptions which go into those models. So, first of all, for all the realistic cases, Carlo and others only consider primordial black holes, which, given that they're speculative, is, I think, a not very strong aspect of this whole business. Second, Einstein's equations are violated. And all of this is done under the assumption of spherical symmetry, which brings me back to my original point about Kerr and realistic astrophysical sources. So, but that's something. It's like a first proposal. Or, well, it's not really first proposal, but it's a proposal on the table, and one could look at it and see which aspects one is happy with and which aspects one is unhappy with. And in particular, one could contrast this with cases of cosmological bound scenarios, in particular the Janus or Janis point. So I guess an interesting thing to do would be this. Assume briefly that this kind of models is something worth having in your theory. Can those constructions be understood as gluing together solution and time reverse in such a way that some suitably chosen relational degrees of freedom will be continuous throughout? Oh, sorry, it's an artifact region A and B.
Sorry, by time reverse you mean that it's just the mirror image?
Exactly.
Because when we go to a Janus point, it's not the same on the other side. Qualitatively, it's
good.
Different.
So I should expand on that. Thank you for this comment. So in the early models, people assume that it is an exact mirror image. So it goes under the name time symmetric. I'm not sure what name they were using. It could be black hole fireworks or black to white hole tunneling or some equivalent of this. But in later models, people started to include additional physical factors, which made the model less time symmetric. So there seems to be some sort of freedom to play with additional considerations. But the way I understand it as a Janus point, as we go through the Big Bang in scare quotes now, of course, some entropy-like function goes to the minimum there. And I think it is not really clear that something like this would happen in those cases. So certainly the area of the horizon doesn't go to 0. At least if we think of this in terms of the Penrose diagram. And also in contrast with cosmological singularities, there is an exterior region here. So that also seems to be different. Okay, but some of you may feel a bit unsafe and threatened now, because all those models, I mean, they make seemingly essential use of white hole geometries. And I mean, of course, most of us seem to be convinced that black hole models are approximately, up to certain idealizations, good descriptions of physical processes in the universe, but white holes do not seem to do so. So one could put it in the following way. Among the known astrophysical sources, there are some which are good candidates for black holes, but there are none sources which are candidates for white holes. So there is an asymmetry in GR between black hole solutions and white hole solutions. And you could ask, what is the source of this asymmetry? And interestingly, one can suggest a sort of dynamical explanation for this. And so it was first proposed, as far as I know, by Erdely in 1974, and subsequently elaborated by further work. And Erdely considers a situation when we have a black hole, which happens at some point, but sort of not all parts of it happen at the same time. So there's some like lagging course of the Big Bang. So regions where sort of the singularity in a way continues, even though the exterior region already behaves like a normal spacetime. And Erdely argued that in those cases, and those lagging cores of Big Bangs are represented as white holes. And Erdely argued that accretion of small amounts of matter around white hole leads to gravitational collapse. And so, in a way, white hole turns black. And this could be an explanation why we do not see anything resembling a white hole. So if we imagine a universe with some initial black and white hole population, those additional dynamical effects will get rid of the white hole population very quickly. And so that could be a sort of explanation for this sort of asymmetry. So yes, this is the sort of picture that Erdely is working with. So that's a diagram for an accreting white hole. Yeah, we have the cosmological region here and the white hole region here. And spacetime is bounded by past singularity here. And yeah, I don't really know why Erdely assumed future singularity, but he did. And then what happens is that radiation flows from the cosmological region to the white hole region, and that causes increase in the size of the apparent horizon here. Yeah, and basically what happens is you get accretion disk around the white hole horizon, because white hole is also a massive object, and this will lead to gravitational collapse. Now, those results are rather old. I think there is research on this sort of ends in the 90s, but you could see that optimistically, like consensus has been reached. We know that white holes are unstable, case closed. And all of this assumes that white hole is non-rotating. So yeah, spherical symmetry again. Now the question is, okay, could we use this sort of results in constraining black to white hole transitions in some way? And if so, does this sort of constraints have adverse effects on whether this whole scheme is as an acceptable way of providing a singularity resolution? Let me start with the remark on the recent paper. So Bianchi, Carlo, and others argued that perhaps white holes which result from transitions are good candidates for long-lived remnants. And if they are a good candidates for long-living remnants, then one could just make standard moves and argue that, oh, I have an acceptable remnant solution, so that provides me with a solution to the information loss paradox, and perhaps it's even better, perhaps at some point this remnant will just transition into ordinary matter, and so then there will be no incompleteness left to be dealt with. And one of the standard problems for the remnant solutions is that there are arguments that remnants are unstable against perturbations. And Bianchi and others have this to say about this. They say that that's true. We admit that white holes are known to be unstable under perturbations. But in their opinion, the instability arises because modes of short wavelengths are exponentially blue shifted along the white hole horizon. But in the case they're interested in, and especially in the case of like primordial black holes, the white hole will be very small, and the way they see the only source for running the sort of blue shift argument for instability is by some sort of Transplanckian perturbations. And if one assumes that there are no Transplanckian perturbations, there are no instabilities to be considered, and so their white hole remnant proposal is better than other available remnant proposals in the literature. Now, of course, your inner Bill Unruh gets worried at this point. What is a good reason to justify that there is no Transplanckian perturbations? And second, I think more importantly, is that arguably blue shift is not the basis for white hole instability. True, Erdely in '74 argued that blue shift is the reason for white hole instability, but subsequent analysis in the literature departs from that, and the consensus which emerged from that seems to be that white hole instability is not due to blue shift, but due to gravitational effects of white hole accretion. And so the argument why the instability is not to blue shift is the following. So consider maximally extended Schwarzschild spacetime. In this spacetime, past horizon is non-compactly generated. So you could have a lot of ingoing from the past null infinity null geodesics, and those accumulate onto the past horizon of the white hole, and that indicates instability in the sense that flux of radiation emitted inward from the infinity would be blue shifted as it propagates along the past horizon. And the reply to that, which as far as I know was first made in Lake and Redder, is that actually if I consider my white hole as embedded in a cosmological model, the past horizon is compactly generated, so there is no accumulation of null geodesics, and so there is no blue shift, and so if white holes are unstable, it's not due to blue shift. Because of the way I think about white hole as embedded in a cosmological model. And then there's a lot of analysis, mostly in those papers. If you're interested, I recommend Barabas, Poisson, and I forgot the third author, for detailed models of white hole accretion. And so that, to me, suggests modification of this story about the life of a black hole. So I would call it cycles, and the advertisement is that white is the new black. So assume that in the white hole phase, classical GR is a valid theory. So in particular, I'm ignoring time reversal of the semi-classical evaporation, but there are some arguments in the literature to the effect that white hole instability also arises in time reverse of the semi-classical evaporation. But assume that GR is valid. So if GR is valid, then if I have some, and it could be a very tiny amount of matter in the exterior region, I could run the white hole instability argument, because I have a massive white hole here, and I have matter around to accrete around it. And so even though my system transitioned to white hole geometry, accreting matter leads to collapse to a black hole. And so the lifetime of a black hole looks like more or less like this. It forms, evaporates, transitions to white hole. By white hole instability, transitions to a black hole again, which may evaporate again. It may take some time, perhaps transitions to another white hole, and then for the same reason recollapses, and so on and on and on, and off it goes like that. So if you grant me the right to apply classical GR in the white hole phase, I could sort of tell you what are some possibilities of what the future evolution of the system looks like. So perhaps mass gain due to accretion and mass loss due to evaporation, and perhaps the transfer, which is all the matter which escapes from the black hole before the accretion becomes strong enough. They could balance each other, so then the black hole size is constant. Mass gain could be larger than the loss, so then the black hole would grow throughout the process. Could be smaller than the black hole size shrinks, and there could be variations. Sometimes gain is larger, sometimes loss is larger, and yeah, then it would be a very strange kind of black hole, which sometimes becomes bigger, 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 then a bit smaller, then bigger again, and so on. So in particular, this sort of black hole, of course, would violate an area theorem, which is undesirable, I think. Note also that this argument for white hole instability is a sort of environmental effect. So it really depends crucially on the fact that we have available some matter in the exterior to form an accretion disk around the white hole. And one could imagine that if you have late stages of accelerated expansion where the exterior region of the white hole is patchwise de Sitter, as per so-called cosmic no-hair theorems, there may be no available accreting material. And in this case, white hole may, after all, transition to regular matter. And we would have this nice singularity resolution that we started with, where observers on the outside, outside the event horizon, would learn about what happened to the matter, to the matter which was lying on the collapsing shell. But this seems to be very contingent, and given given speed of the expansion, not something we should expect to happen anytime soon. So this, I think, is one of the ways to constrain this sort of approaches, and the constraint just assumes that I have classical GR I can trust in certain regime, and that a bunch of classical old results can be applied. Now, there's a lot of folklore about white holes. So part of the folklore is that white holes violate second law of horizon thermodynamics. Because the area of the horizon of a white hole is non-increasing as we go to the future, because area of classical black hole horizon is non-decreasing per the area theorem. And so in this way one could say, if I have a white hole solution, it violates second law, so it's unviable. But opinions on that vary, and I see no principled reason to adopt this or that position. So for instance, Klaus Kiefer doesn't think that white holes violate second law, because he considers second law to be a statement about future horizon of a black hole and past horizon of a white hole. And so, if so, yeah, sure. Why would we expect that future horizon of a white hole satisfies the area theorem? And there are some concerns about other arrays of time. So, for instance, they argue that white hole would require coherently incoming advanced radiation in order to grow hair. So the idea would be that, if I have a white hole's time reverse of black hole, it also satisfies the null hair theorems. But once the sort of stuff starts to come out of white hole, it would grow hair because it would be characterized by baryon number and so on. And so white holes for Z seem to be incompatible with the radiation arrow of time. But I think this sort of concern also doesn't really work in the case of those models, because we have some feeling and some idea about what sort of stuff and matter we have close to the apparent horizon, and then we could just say whatever comes out of white hole is what has fallen in a way. And so literally, null hair theorems would not be valid. Consider now generalized second law. That is the statement that generalized entropy, so for instance, the area of event horizon of a white hole plus whatever is being emitted increases with time. Aaron Wall recently formulated a particular version of generalized second law and used it as a replacement for null energy condition to formulate a version of quantum singularity theorem. So I think, and a bunch of other interesting results. So an interesting thing to look at would be whether a no-go theorem, which assumes validity of generalized second law, could be proven against black to white hole transitions. But prima facie, that doesn't seem obvious, because we have this S out term in here, and we can always say, oh yeah, well, whatever entropy we lose from the white hole event horizon, it's just being transferred to the exterior, and so GSL could be valid. It's an open question. I have no answer. I hope to have an answer at some point, but not yet. But here's a totally speculative part. Assume that Wall's quantum singularity theorem holds, and assume that black to white hole transitions per se do not violate GSL. Then prima facie one could take this singularity theorem and argue that it actually applies in sort of within the event horizon of the system, particularly for the cycles models that I presented. And so if that could be done, if there would be a reason to, in other words, if the premises of Wall's quantum singularity theorem would be satisfied in the interior of this cyclic system which transitions between black holes and white holes, we could have something like an answer to the information loss paradox, and we would have the reason, or perhaps hand-wavy, but a reason for violating premises of classical singularity theorems, in particular null energy condition, but we could still have incomplete geodesics in the interior. And so, again, going back to the list of what a singularity resolution should do, depending on how ambitious you are, and if this sort of statement is true, we could have singularity resolution which leaves us with a singularity in the interior of the system after all. And that's it. Thank you.
Okay, we've already had a couple, but stupid questions first.
Yeah, I have a question about the you motivate actually your talk with actually the information loss. But personally, I don't understand it. I mean, because when we actually throw the book into black hole, and of course, black hole, maybe, I mean, the black hole actually observe the books, but outside the black hole, already we disturb the all like the distribution of gravitational force, whatever field, and then we can trace the information outside. But why? How come actually all information is completely gone? Actually,
I mean, no one knows if it's completely gone.
But
like,
it seems to be it's never completely gone. But if people believe,
well, if your book crosses the event horizon, then you cannot recover it from the outside.
Yeah, book we cannot recover book. But what about actually already interaction book and already had interaction with other like field or and still you can trace detect the field, could it gravitational field or whatever outside, and then you can trace the information. Yeah.
Well,
I mean, everyone said no, but this looks information cannot actually some information in local actually area already related to some next to local like space time. So how?
Well, no, I think mostly we just imagine, something like it, pen drive with my slides, or we just. And so. Well, depends what you mean by localization. The US. It contains a lot of information, and I think it's pretty time. And why not?
The library has the information also outside the library if you actually trace all.
Okay, guys, this is degenerating into the black hole information loss paradox, which is somewhat separate from the talk that's under. I mean, it's an interesting discussion, but let's deal with issues in the talk first, and we'll come back. Okay, general questions on the talk.
Are there known initial value data whose forward evolution creates white holes?
I mean, so it's really difficult to think of white holes in terms of initial data which generate them, because unless your white hole transitions to the emerging expanding shell, it makes no sense to speak about Cauchy surface. So in this sense, you cannot really treat this like this sort of classical white hole business in terms of an EVP where your initial data give rise to the white hole solution in the future. Because you won't have a Cauchy surface unless the white hole already transitioned to ordinary matter.
More questions? To briefly return to Enrique's point, also if you time reverse that solution, right, it would be information coming out of black hole.
Yeah, that's one way to look at it.
Yeah,
that was
I mean, I've never regarded white holes as physical. That's part of the point of this question.
That's really naive. Do you want to answer less naive?
Let's have naivety first.
So this, why wouldn't you think that if you had bouncing cosmology, from our perspective, the things that in the other half of the bouncing universe we'd call them white holes? In a sense, there's not something mysterious about it. It's just what we'd identify from our arrow of time in the other side of the bounce. What people in that side of the bounce would call black holes, and they'd call our black holes white holes. Isn't that a reasonable understanding of what they would mean?
Sort of, I guess, depends how you set up the arrow of time in the second part of the solution. I see no principled way of doing it this or that way.
So if we imagine a bouncing cosmology where the arrow of time is like in Julian's model of Janus, wouldn't people on the other side just call our black holes white holes? So it doesn't seem like something so unphysical.
No, not necessarily, right? So I have a black hole. So I have in that model I have Big Bang here, and expansion here, and then expansion here, right? And then what would be a candidate for white hole?
So I mean, we would identify in the other branch what they would call.
That sort of depends how you.
If you glue two, suppose you have our universe and a black hole forms in it, and you just stick a mirror at the Big Bang, okay, and then you conserve the idea of time from one side to the other.
Oh yeah. If you do that, then I think that's absolutely right.
What do you mean by a mirror at the Big Bang?
You just glue two solutions together with t goes to minus
Yeah.
t. Absolutely artifacting.
Yeah, it's totally arbitrary.
But for function singularity, is there a horizon?
Right. So I guess we imagine a situation when we have a cosmological model with Big Bang and black hole formation inside. Evolve that from some initial data to the future, and then glue time reverse of what we obtained in this way there. And then, I guess if you demand that the arrow of time points sort of like ours does, then that's right. Then what we call black holes, they would see as white holes and so on.
But is there a horizon for function singularities?
For a big crunch singularity? Yeah.
But if you took the Hamiltonian formulation you've seen in previous talks, and the Hamiltonian is chugging along and telling you universe what to do, there's not going to be any bounce or anything. It's just from the one which is collapsing, it's just going to run into a singularity. The Hamiltonian isn't going to give you a bounce.
It's some kind of quantum process.
Yeah, I mean, we're talking here, the models Juliusz is really talking about are these loops-inspired things, where there are bouncing cosmologies and there are black hole, white hole transitions, and physics beyond GR.
Right. I mean, I don't see how one could get that without this sort of moves.
So what are the constraints on what you can do?
Okay, address your question.
I think that's a good question. I think there are very few constraints in a way. But so, what I argued is just that if I just can trust classical GR, then I could provide one sort of constraints on what the future of such a transition looks like. But I think it sort of goes back to Steffan's point that if I don't have a very good physical control over what happens in those A and B regions in here, then I can make a lot of weird stuff happen. And in particular, all the nice and standard techniques of excising points and gluing this or that solution. In principle, they are available, and additional argument is needed to rule them out. And I think it's really hard to make those arguments on basis of some principle. Yeah.
I'm still trying to get to grips with black holes and white holes and things. I'm very ignorant about it. But the one thing that really struck me reading the Anderson-Rendell paper where they prove the BKL conjecture in the quiescent case, and they say that, they don't consider going through like we do as a Janus point, but they say there's an open neighborhood on sort of our side of the space-like singularity that's the Big Bang, which is CMC foliable. Does that mean that there won't be any primordial black holes in the classical theory there? And that they all come about through standard evolution? I mean, already just in the n-body problem, we see something a little bit like a black hole formation when you get the clusters formed. In the three-body problem, the Kepler pair which forms is, so to speak, not totally unlike a black hole. And that just everything happens away from the Big Bang, and that and that it's quite a way into the evolution of the universe before any black holes form.
I'm not sure I have an answer to that.
No, I'm throwing it out really as a thought.
I talked to Hal Haggard a little bit about this, and so if I understand correctly, just a little bit in their defense, you can make of it what you will. He is looking for these two boundaries and have a semi-classical transition. So he's trying to find a solution, like a complex solution of space-time metric, for example, that has these real boundaries. But that would indicate, as a lot of people do in this semi-classical approximations or tunneling, etc., where you find a solution which is complex, and that represents some kind. And Steffen has worked on this. Maybe he can talk more about it. But yeah, that's my understanding.
Do you want to answer that, or is it just?
Do you want to answer that, Steffen?
Well, I think Steffen has his own question anyway, right? So,
no, I mean, in response to the previous point, I'm not sure I have much to add. I mean, it's a picture, of course, to think of this as a kind of tunneling process, and to describe that perhaps in a semi-classical approximation. And if that works, that's nice, and it would be an improvement because you wouldn't include sort of this arbitrary violation of Einstein equation. So I would be happy about that, but I don't think I have anything else to add to this.
Yeah, I mean, I guess one could also try to see whether violations could be bounded from below. That would be cool, but yeah.
So my question was a bit different. With this instability problem, I'm still a bit puzzled as to how I'm supposed to think about this physically. So in this scenario, are there any statements about the size or the mass of these white holes that are being generated? At some point you mentioned that they had to be Planckian. But then they're just remnants of some sort, which you can call white holes or something else.
Yes, so so the way I would put it, and insofar as I understand what they're doing, is the following. So the picture is completely general. Like this gluing process doesn't care about properties such as mass of black hole or whatever. It's just that they have the expectation that only if this is very small, the transition's amplitude will become probabilistically relevant. And this is why, sort of implicitly, in most of the discussions, they just restrict very small primordial black holes, which are expected to evaporate within reasonable time frame. But yeah.
Okay, but then I would just say this is some kind of remnant scenario. Because then if you have these Planck-sized objects, and they do whatever they do.
Well,
I mean,
yes, and I think like this paper is basically an interpretation of this along with as a remnant solution. And so then, like, if you run these arguments, one can show that despite what they say, actually the remnants are not stable. So that's this part. That's one way of looking at it. Yeah.
Okay.
Yeah. Great. Yeah, that's great.
I just want to make a comment. If we can go back to that picture you had. The one with the chain. Yeah.
This one.
It doesn't represent the real universe, because in the real universe there's an initial singularity which is space-like. Then
right.
The real universe is in vacuum, and then stuff keeps falling in. So in the real universe, any real black hole is formed by stuff accreting, and after it's formed, there still continues matter and radiation accreting into it, and everything looks completely different in this picture.
Yes, and I'm very happy that you say that, because I think this is one of the reasons why the accretion around white holes is really important in the actual reasonable context.
Well, I've written a few papers with a young Iranian colleague about this, trying to get a more realistic picture. One of the things that happens is that you get a pair of apparent horizons, and the outgoing horizon is null, and null. It becomes space-like because of the matter which is falling in.
I'll have to ask you for reference on that.
Just to demonstrate, you don't think this is would be even a useful time model if they are able to define it?
I personally just find, so if you're going to violate Einstein equations, you can wave your hands and say anything.
Yeah.
Any last questions?
So let me just have a comment on this. So if we go back to what I had as a list of sort of what could it mean to have a singularity resolution, what you just said is essentially that if I'm looking at this line number 2, I may want to avoid this or that premise of singularity theorems, but not validity of energy conditions or Einstein's field equations.
Look, if you follow the loop quantum gravity thing and you say, I've got a process whereby you approach, you go through it. Then we've got a proper theory, okay?
Okay.
So I think maybe underlying what this is the hope that there is such a theory.
Yeah.
But I would like to see it embedded in a real astrophysical context. That's what I would like to see.
Yeah, me too.
Okay, let's thank our speaker again for an excellent talk.
Thank you.